This experiment is titled Impact Speed. The goal of this experiment is to estimate the speed of falling object as it strikes the ground and relate it to Newton's second law of motion. Specifically, we want to determine how air resistance and human reaction time affect the object's actual speed and compare it to theoretical speed. We drop a tennis ball and a ping pong ball from a height of 1.574 meters. Using gravity at 9.8 meters per second squared, the theoretical fall time is 0.567 seconds, and the expected speed is 5.57 meters per second. We measured 0.28 seconds for the ping pong ball and 0.22 seconds for the tennis ball. These shorter times made our computed speeds a bit higher than expected, showing that manual timing has human reaction errors. But both balls still accelerated because of gravity of Newton's law of motion that objects speed up when acted upon by unbalanced force. Here are our recorded data and computed values. The theoretical fall time and speed were calculated using the formulas T equals the square root of 2 height over gravity, and V equals to square root of 2 gravity and height. As shown, our measured times were shorter, leading to slightly higher calculated speeds. How your teacher overlap your graph with those of others? How does your actual speed versus time curve compare with theirs? Our actual speed time curve is higher than the theoretical curve and those of others group. This happened because our measured times were shorter, which made our computed speeds look faster. The difference shows human reaction error during manual timing. What can you say about objects whose speed versus time curves are close to the theoretical speed versus time line? Objects with curve close to the theoretical line were measured more accurately and were less affected by air resistance or timing errors. Their acceleration is closer to the expected value due to gravity. What does the area under your speed versus time graph represents? The area under a speed-time graph represents the distance traveled by the object over the specified time interval. The equation for distance traveled is distance equals to velocity in time. In this log, the distance fallen is the same with or without air friction. How do the average speeds and times compare with and without air friction? Without air friction, the object falls faster and has a shorter time because gravity acts freely without resistance. With air friction, the fall takes longer, and the average speed is lower because the air slows down the motion of the ball. If you drop a large leaf from the Empire State Building, what would its speed versus time graph look like? How might it differ from that of a baseball? The left's speed versus time graph will rise quickly at first, then flatten into a horizontal line, showing that it reached terminal velocity because of strong air resistance. The baseball's graph, on the other hand, will be steeper and take longer to flatten, since it is heavier and less affected by air resistance. The terminal speed of falling object is the speed which it stops accelerating. How could you tell whether an object had reached its terminal speed by glancing at an actual speed versus time graph? You can tell an object has reached its terminal speed when the speed versus time graph becomes a horizontal line. The slope or gradient of a speed versus time graph represents the object's accelerating. When the graph is a horizontal line, its slope is 0. Since the terminal speed is defined as the speed at which the object stops accelerating, meaning net force is 0, the graph leveling off to a constant value for speed visually confirms the object has reached this point. In this experiment, we learn how gravity and air resistance affect falling objects. By dropping a tennis ball and a ping pong ball, we observed that the lighter ball fell slower because of air friction, while the heavier one fell faster. Our results showed how air resistance influenced the motion of objects, helping us understand Newton's second law of motion. and the relationship between mass, acceleration, and gravity. This experiment made us appreciate how physics concepts apply to real-life situations.